If you attended the past community hours or community showcases that we had, you probably have good familiarity with cloud computing, but I thought it'd be worth taking just a slide to talk about what cloud computing is in case folks are here who had not attended the past sessions. So cloud computing is your analysis and your storage in this nebulous space called the cloud. And that can be on the Amazon Web Services or Google Web Services, or Microsoft Azure, you may have heard of as well. And the big advantage here is accessibility. And so your storage and your computation can take place in this nebulous space called the cloud, using your cloud buckets and using CPUs elsewhere out there and not locally. And so this allows kind of this glass wall where you can use web applications or APIs, command line calls to access computational resources elsewhere. And NHLBI's BioData Catalyst, which is the ecosystem we're talking about today, is built in that cloud. So all the tools you need are up in this nebulous space called the cloud. And so you can access that really from everywhere. Next. We can draw this comparison between cloud computing and local computing or your high performance cluster. That might be where your familiarity is right now, is with your institutional cluster. So let's go through kind of the differences here. So cloud computing is faster and more scalable than the high performance cluster. It's faster because there's more resources available. Amazon Web Services or the Google Cloud just have an enormous number of CPUs that you can scale to an enormous number, enormous amount of storage. And you can scale that as you need. So maybe you only need one CPU or 5 CPUs for quick testing, but then when you want to run it, you want to scale up to hundreds. So it's quicker to change. It's also easier to collaborate. An anecdote from my own life, I had a friend at an institution that was working on their cluster and had their data stored there. And it was actually faster for him to download his genomes to a hard drive and mail that hard drive than it was to find a way for his collaborator at another institution to access his server. The cloud gets around that because everything is stored in the cloud and you can control access and permissions, which is the next point. So for access, you can control and allow collaborators to access, and you can get into the cloud from any laptop that you're on as long as you have internet, or from your cell phone if you choose to do computing or log in from your cell phone. And it's on a use what you need basis. So this is really where costs start to come in, where you're just paying for what you need as you need it. Maybe it's that one CPU for testing, maybe it's 1,000 CPUs to quickly run through a 50,000 patient sample. We can compare this then to the high performance cluster where there's upfront costs where these servers need to be built. This is typically borne by the institution, but you might have to pay subscription fees as a PI, or maybe your lab pays that for continued maintenance. So maintenance costs on your home institution's HPC, you have to update packages regularly, failed hard drives, etc. And those might be covered by institutional fees, or these are costs behind the scene. And then one other point I wanted to make is that on the cloud, you're not going to be stuck in queue. There was a job I was running one time in building a genome where I had to wait 2 days because I needed a whole node and there was a lot of people in front of me using a node. So I was stuck in queue for 2 days. On the cloud, it can be instantaneous and you can get your analysis done fast. Next slide. So where do the costs come from if you're doing cloud computation? There are two really categories of costs that we'll discuss later and talk about optimizing and benchmarking. So one is computation and the other is data storage. So computation, the number of CPU hours, if you work on an HPC, you're probably familiar with that. The other is instance type. So there's on demand and there's something called spot or preemptive instances. And it's kind of, this is technically different, but it's kind of like a bidding process where you can optimize and reduce your computational costs by selecting spot or preemptible instances over on-demand instances. The other costs are from data storage. And so there's two kinds of data that we'll talk about, hosted and derived data. So the NHLBI top med datas are hosted data. So that means NHLBI is paying all the costs for holding that in cloud buckets, and you can access those without having to pull them to your local computer or without having to pay for what those data sets cost to store. Derived data, which are intermediate files or endpoint files that you're storing in the cloud, or if you bring your own data, you do have to pay for storage costs. And then the final point for data storage costs are egress fees. So if you have data stored in the cloud and you need to pull that data out, there is cost associated with that. I also want to note that BioData Catalyst is integrated with the NIH Strides initiative. It's an initiative to help researchers get into cloud computing and have better access. So there are discounts through Strides. We're not going to go into details about NIH Strides today, but if you're interested in joining BioData Catalyst, we can talk about that. Next. So before I give it over to Paul to talk about how you can get cloud credits to run pilot studies, I just want to really emphasize our value here is that there's no need to download large TopMed data sets and then upload them to your own HPC so that you need to manage that data and take up storage at your institution. Those are hosted. There's no computer system to manage for you or your institution. You just log in from your laptop into the cloud and run it. The ecosystem itself is supporting the packages and updates, and then you're only paying for what you use. So if you're only using one CPU for quick testing, costs are low, right? And as you scale, costs scale with you, but are still relatively low compared to keeping a cluster.